Do you have any questions? All right. So I want to start with rediscussing the idea of the optimal game that we talked about last time. So we will discuss two games, okay? Two kind of games. So the first one is you toss a die, all right? And if it's 1 to 5, then you win exactly that amount. If it's 6, right, then you get 0 and you lose the game, okay, and quit. Here you have the option to redraw. But if you redraw, then you lose the winning so far. Okay, so for this kind of game, basically the most you can win is $5, okay, for each round, because you cannot carry your winning from the previous round. The second one is going to be similar to the first one, but winning is cumulative. In other words, you can carry, right, whatever you win from the previous round to the next round. Of course, the catch is that at each round, if you roll a 6, then you will have to quit, okay, and you lose everything. Without that condition, then everyone will just want to keep re-rolling and keep getting more and more win. All right, and then there are two variations of each of these games. Either the finite horizon, where you can only toss so many times, or perpetual game, where you can toss as many times as you want. So ways to approach this problem is like this. So again, right, basically because of the choice to redraw and continue, this is exactly an optimal stopping problem, or like a dynamic programming problem. So for the finite horizon, you always want to go immediately to analyze the game at the last moment and continue back in time. Right, this is exactly like option pricing. Okay. With the perpetual game, then there's no last moment for you to do some analysis on. So what you want to do is you need some observations. So there's no fixed method here. No fixed method. But the general guideline is, first, that the game value only depends on current fortune. And not time. Okay. The second one is this, that in this current fortune, you can always divide the fortune, the current fortune, into two sets. Stop and continue. All right. Basically, you want to analyze. So you want to analyze the game depending on your current fortune says that you should stop, or your fortune says that you should continue. Basically, if you know these two sets, if you know what they are, then you know the game, or then you understand the game already. Okay. In the stop set, okay. In the stop set, for the fortune, right? For any fortune, and in the stop set, then the value of the game is n, because you decide to stop there. So whatever the value of the game is worth for you is exactly that fortune. For fortune, right, in continuation set, we do not know Vn, right? That's for you to find out. But we know that it must be at least n, and it equals its continuation value. Okay. The fourth observation is, if n is in the stop set, then k is also in the stop set for k bigger than or equal to n. What does this mean? If at some fortune you decide to stop, then rationally, if you have a higher fortune, you must also stop. You cannot continue, you cannot somehow decide to continue at the higher fortune, yet decide to stop at a lower fortune. Because, right, when you stop, the value of the game is n. So if it's good enough for you to stop at n, it must be good enough for you to stop for any value bigger than n. Similarly, right, conversely, for k in continuation set, sorry, n. What do I mean by this, right? Basically, if you are in a continuation set, then this is the opposite, right? If, right, you decide to continue for some value n, then you must continue for some value below that, because n is not good enough for you, right? So then any value below that should also not be good enough for you. All right. With that observations, right, these four observations, I'll show you how to apply them to these two games. So the first one, okay, remember game one is that you do not carry your winning to the next round. Each round is a fresh payoff, okay? So game one, right, we have shown the finite horizon approach, right, the finite horizon game. Okay. I made a mistake in the infinite horizon last time, in the perpetual game last time. So I want to correct that. All right. So what is my mistake? So first of all, right, according to this principle, game value only depends on current fortune. Actually, it's very simple, right? Think about it. You start out, right? You can roll 1 to 6, right? At 6, obviously you get 0, so forget that, right? That's clear. But then here at 1 to 5, what do you do? Well, you want to think whether or not you want to redraw or you stop. However, though, right, here, say at 1, if you decide to redraw, you don't have to worry that 2, right, will be, I don't know, like your last step, right? So for example, if like you have a Find Horizon game where you can only draw twice, then the analysis is very simple, right? Once you roll, then you look at the next round, and that's your last round. With the perpetual game, right, what happens is you can look at the infinite horizon after that, and your action should reflect that you have no horizon waiting for you. You're not forced to quit, right, at any one point by time, except when you roll 6, okay? How does that affect anything? So first of all, right, that basically, let's say, so first of all, right, let's say this, the challenge here, right, the challenge is to decide, right, between 1 and 5, which one is stop, which one is continue, okay? And basically, again, I guess I want to say that the value of the game is a function of only these values. Okay. So if you roll 1, what's going to be the value of the game to you? If you roll a 2, what's the value of the game to you? If you roll a 5, what's the value of the game to you? Is that okay? And then we'll average this out if we need to. Any question? So for example, among these 5 values, which one is an obvious? Which one has an obvious conclusion? Is there any value that you would say is obvious to continue or obvious to stop? So here, if you follow the game, you see that 5 is an obvious continuation. Oh, sorry, it's obvious stop. Why? Because you don't get to carry your fortune to the next round. So if you continue to play, then 5 is the best you can do. So if you roll a 5, you should obviously stop. So V5 is equal to 5. Is that okay? Now, what about 4? Do you stop at 4 or continue? So 5 is stop, okay? 4 is stop or continue? Now you may think, right, that okay, I will analyze, right? I will analyze the next step. I'll analyze the next step, something like 1/6 times 1 plus 2 plus 5, right? And compare that with 4 to see if it's bigger than or less than. This actually was my mistake last time, okay? I was comparing this with this, and that's wrong. What's wrong is this. This is the one-step analysis given, right, that, somehow that's what you face as a last step. But that's not true, because after you roll the next time, right, suppose you roll 1, that doesn't mean that the game value is 1 for you. Why? Because you have an option to re-roll again, right? So even if you roll 1, that doesn't mean the value of the game is 1 for you, okay? So exactly that here, right? V of 1 is the value of the game. So in some sense, you think of the die as the underlying, as a stop value. And V here is the option value, right? What you will face is the option value. You're not facing the stop value itself. So this is wrong, okay? So this comparison doesn't work. Or actually, it's incorrect. But what do? We do not know, okay? We do not know whether, right, 4 is a continuation or not. And we don't have like a finite horizon, a last time, right, where we know that you must stop there and then come back. So here, right, this is where I say there's no fixed principle, no fixed method in general. You just have to kind of think about it. But here, there's a way. The reason is this. Let's suppose, okay, that 4 is continue. What can we say about this? If you continue at 4, right, then by the observation above, first of all, that means you 1, 2, and 3 are also continue. Because if it's not good enough for you at 4, right, if collecting a 4 is not good enough for you, then you collecting 1, 2, or 3 would not be good enough for you. So you would reroll at these values as well. If that's the case, right, what are you facing? What you're facing will be, right, the value at 4, right, which is the game value when you roll 4 from the first step, will be, right, 1/6 times the value at 1, value at 2, all the way to value at 4, and then value at 5 is 5. Okay. What am I saying here? What I'm saying, right, this is the value from the first toss. These are values at the second toss, right, after you continue, because I assume that 4 is continue, right? So if you continue, right, then you will pick up these values after the second toss. Because 5 is a stop, then that's 5, all right? And because at 4 you continue, right, so the value of the game for you at 4 is exactly a continuation value, all right? Now that seems mysterious because, okay, what does that even tell us, right? Because these guys are still unknown. We know that, like, under this assumption, then V4 must be bigger than or equal to 4, right? But we don't know anything else than that. But actually, because of this conclusion, that you also continue at 1, 2, and 3, right? You also have this conclusion that the value of 3 will also be the continuation value. So at 3, you also redraw, and if you redraw, you will face this. Okay. Again, what's the reason? The reason is if 4 is not good enough for you, then 3, 2, 1 also are not good enough for you. So the value of the game at those points will be continuation value. But if you continue, right, then exactly these are the values you will pick up on the next round. All right. Question? All right. No, right? So this analysis is very delicate, right? First of all, I say 5 is a stop point because it's obvious from intuition. Why? Because again, think about the game, right? Yeah, it's a max payoff in some way. That's right. But if the game is cumulative, then, right, definitely 5, you don't want to stop yet. Who knows, right? It's because if you continue from 5, what do you expect? At most 5 again, right? Because the next time you will roll 5, you have to stop at some point. Do you agree? So 5, right? So, I mean, like, just common sense, really, right? If this is the game that you're playing, if you roll a 5. I bet if you just think about it for one moment, you're like, okay, right, that's the most I can get, quit. So I do that from that continuation. But 4, right, again, just put yourself into a 4. If you roll a 4, will you stop? It's hard to say, right? Because a greedy person may say, I don't know, I may roll a 5 next round. Yes? So that's why, right, this analysis must come into play to carefully see if continuation is a good choice or not. So here I suppose, right, it's a continuation, right? But 5 is clear. 5 is clear. 4 is unclear. Is that okay? So, but then, right, the surprising thing is, by logic, if you continue at 4, you would continue at 1, 2, and 3. But if you continue, then exactly you face these values. So the amazing thing is the value at 4 will be equal to value at 3, equal to value at 1, because they are the same continuation value. Why? Right? Because the game just repeats itself. Okay, the way we structure the payoff makes the game repeat itself. Okay, but then, right, because these are all equal, we can solve for them explicitly, right? We can solve for them explicitly. In particular, you see this is 4, this is 4, 6, right? So something like 1/3, right? V4 is equal to 5, 6. So V4 is 2.5. Does that work? Well, the answer is no, it doesn't work. Why? Because to qualify as continuation value, then it must be at least 4. If it's not, if the value is not at least 4, then you don't want to continue. So therefore, right, V4 equals 2.5 is a contradiction. So this analysis shows us that V4 at 4 you should stop, because if you continue, that implies you continue everywhere else, and it leads to a contradiction. So therefore, right, 4 is stop. Okay. And continue in this manner, right? But then you say, you suppose, right, 3 is continue, you repeat, right, the same argument. You will see that actually if you suppose 3 is continue, then V3 is 3. So that's correct. So in other words, 3 is exactly the boundary where whether you stop or you continue, it doesn't matter. Okay? So V3 is correct. So in other words, right, what have we concluded? That if you stop, sorry, if you roll 1, 2, or 3, you continue. If you roll 4 or 5, you stop. If you stop, right, the value of the game will be 4 or 5 to you here. The value of the game, right, because of, you know, this argument above, for the continuation set, they're all equal. They're all 3. Okay. How much is this game worth then? So value of the game in general will be 1/6 times 3 plus 3 plus 3 plus 4 plus 5, which surprisingly is exactly $3. Okay. So for a perpetual game, this is the optimal strategy, and is you can play $3 if you're risk neutral to play this game. All right. Now compare this. Okay, this is higher than the value obtained. with the finite horizon game. Okay, which makes sense because, here you always have the option to redraw. There you only can redraw up to 3 steps, for example. Also, right, notice the optimal strategy is quite simple here, right? If you roll 4 or 5, that's it. So basically, right, you can tell whoever plays this game, perpetual game, that keep rolling until you got 4 or 5. Or of course, if you go bust, right? If you get a 6, then that's it. But keep rolling until you hit 4 or 5, right? 3 actually is okay too. 3 can be either continue or stop, doesn't matter. With the finite horizon game, then the stopping rule is more complicated, right? It depends on where you are. If you're at step 2, you may want to stop if you roll 4, 5, whatever. But if you roll at step 1, right, the stopping is very different, for example. Any question? Okay. So now I want to go back to game 2, right? But game 2, the winning is cumulative. In other words, right, if you roll $1, oh, sorry, but if I do this, it's going to be too big. Winning is cumulative, but winning, right? But the winning is this. I want to squish it, so it's easy. 1, 2, 3, 4, 5. If you roll any of these values, you get $1. Okay. But winning is. So basically, if you don't roll 6, you pick up $1. If you roll 6, you go bust, and you quit. All right. Otherwise, the accumulation is too big to conveniently analyze. That's all. So let's analyze game 6, right? Game 2, but perpetual. Okay. So basically, right, someone draw a die. And if it's 1 to 5, they pick up $1. If it's 6, they quit and they lose everything. They can redraw, right? They can redraw and then continue. So the question is, right, actually the question is very simple. When do they stop? At what fortune do they stop? Okay, is there enough? Is there a good enough value, right? So, and if at that point, right, what is the value of the game to them, right? So first of all, right, same idea that value of the game will be a function of current fortune. On the other hand, though, right, notice it's quite tricky here. The current fortune, right, will be anywhere from 1 to what? There's no max fortune here yet, okay, as far as we're concerned. Why? Because, right, there's, at least from the first consideration, there's no upper bound on how much the whoever plays this game can win, right? Theoretically, they can win $1 million for all we care, right? If they keep rolling 1 to 5 1 million times, of course the probability of that is 0, right? Close to 0, but they can't, right? So what is this? All right, but we suspect, right? We expect that there is a n, okay, so that v, right, so that we stop, right, if n is bigger to n, and continue if n is less than or equal to n. Sorry, less than n. Okay. Now, this is, I think, intuitive. Basically, right, this is what I say where in this second game, right, the basic question for someone who plays this game is, when do I stop? How much is enough? How much is, like, after I accumulate, right? Because again, the person in game 2, every round face a loss, right? And that loss is just going to grow larger, right? As they keep on winning. So at some point, maybe the loss is too much, right? And they're just gonna should quit, right? Quit when you're on top or something. So what is this value, right? What is this sweet spot, right? Where they should quit is the question, okay? So, and also you see, right, it's consistent with what we say here, right? That basically, if there's a stop value, then you should stop for everything above that. And you should continue, right? If there's a continuation value, then you should continue for everything below that. Also, one more thing, right? From the realistic point of view, right? The player will never enter above big N to begin with. Why? Because at each point, right, he or she only win $1. So the scenario, right, will be something like he or she may at n when n minus 1, and right, if they roll 1 to 5, then they move to n and they stop, and that's it, right? They will never move to n plus 1 to begin with. Is that okay? So how to figure out this n? Well, what should this n be? It's a stop value, so Vn, right, must be equal to n. That's true. But on the other hand, it must be higher than its continuation value, right? Otherwise, you won't stop. So it should be bigger and equal to, right? What is the continuation value? If you continue, right, then you pick up 5, 6, n plus 1 with probability, right? Sorry, so you pick up n plus 1 with probability 1, 6, right? But sorry, 5, 6, right? Because if you roll 1 to 5, and you pick up 0 otherwise. So this is the expected payoff, right? If you continue. And if you want to stop, that would be satisfied. So in other words, right, that what is n here then? So 1, 6 n, right, is bigger than or equal to 5, 6. So n is bigger than or equal to 5. So in other words, actually here is quite simple. At 5, the person should stop. Okay. So what about, so now so basically then, right, what this says is you should only figure out the game for 1. So we should only figure out the value of the game for V1, V2, up to V4, right? Because V5 is equal to 5. Okay. What's the value of the game at 4? The value of the game at 4 will be, what do we want to say here? The value of the game at 4, right, will be continuation value, because we know that they will continue, right? So it will be 5, 6, right, times 4 plus 1, which will be 25 over 6. And notice that's bigger than 4. The value of the game at 3 will be 5, 6 times 3 plus 1, which is 16 over 6. And that's bigger than, hold on, what I'm saying, right? 20 over 6. And that's bigger than 3, V2, right, etc. 5, 6 times 2 plus 1, which is 15 over 6, is bigger than 2. And V1, right, is 5, 6 times 1 plus 1, which is 10 over 6, is bigger than 1. V0 is exactly the value of the game for us here. Why? Because starting out, we have nothing, right? So that would be 5, 6 times 0 plus 1, which is 5, 6. So the game, right? The game value, surprisingly, is only 5, 6 for you here. Okay. For the perpetual game. And you should keep rolling, right, until you hit a 5 or go bust. Until you get $5, right, or go bust. whichever comes first. Any question? All right. So I think I'll stop here. All right. I mean, you can see that you can invent as many games as you want, right? With many crazy structure of payoff, right? Cumulative payoff with different kind of, payoff depending on the outcome. Maybe accumulation, but up to the most recent two games, who knows, right? Final Horizon game, right? Perpetual game, that kind of stuff. The analysis, right? Like I said, the guideline. If you follow the guideline, you should be able to crank out, right, what the game is worth. But the analysis depends on the structure of the game. Could get quite hairy. But I think it's kind of fascinating on how you can just deduce logically how, right, you would play optimally. Again, of course, under the assumption that the player is risk neutral. All right. Okay, so enough of that. Now we're done with discrete models. We're going to move to continuous time model. Right, Black-Scholes model, which is chapter 5. Okay, and then I guess with chapter 6 too. So first, let's take a look at the motivation, or how Black-Scholes model, right? How Black-Scholes model can come. So basically, okay, what happens is this. Suppose you have a time horizon, 0 to t, all right? And you divide that into, let's say, n periods with, right, and with delta t equals to t over n. Starting at time 0, you would draw a tree, right? You would draw a tree with n steps. Okay, and to get to n, to get to big T. Okay, the question is, what happens to this picture as n goes to infinity? All right, so the interpretation is that, right, remember, the more steps in between, that means the more, right, action that can be taken, the more, activities that will happen in between. And so if you take this to be like, let's say, I don't know, 30 days, then if you divide into 30, that means action can be taken on a daily basis. But if you increase the number of periods, right, basically that comes to something like instantaneous trading, for example, right? That the stock moves, the stock price get updated every single second, right? And even beyond that, okay? If we push that, then how does the picture behave? Now, of course, what comes to your mind is some kind of like really crazy picture, right? Like trees that can grow really large, like almost like a, like a blacked out picture. Well, that's not the picture that we have in mind. The reason is this, right? Even though we draw the tree like this, the tree is an overkill, because the tree tells you all possibilities from 0 to big T, which, right, of course, there are 2 to the n possibility, which goes to infinity really quickly. What happens is actually, right, among all these possibilities, there will always be one scenario, right? There will always be one path that get realized where the other path don't get realized. Yes. So what we're asking is what happens to the path, rather, right? How does the path look as n goes to infinity, okay? And as you see, I was doing this squiggling right here. What the path might look like is something like this, as the tree, right, as the step size goes to 0. And that looks more and more like the typical stock size, price that you see in real life. One thing that you might have seen as well is something called the Brownian motion, okay? The Brownian motion path. Which also looks something like this. So in fact, the two have an intimate connection, that the Brownian motion is the driving force behind, right, the limiting effect as n goes to infinity. Also, as n goes to infinity, right, I said we have instantaneous trading, or basically, time becomes continuous. All right. So all of these is what we want to describe, and we want to make precise, all right, and build it up to the model. So first, right, let's analyze this in terms of mathematics. The mathematics is this, okay? So S0, sorry, we have this, right? Sn will be S0, x1, x2 times xn, okay? Now, do remember that basically before, right, we didn't care. We just say that xi are iid with up and down. In reality, right, this up and down must depend on delta t, okay? Why? Because they are percentage return, all right? I didn't care so much to emphasize them, so I did not kind of scale them as a number period grows, because we never really go beyond like 3-4 periods anyway. But to be precise, right, the return on each period should depend on how long that period is, right? A stock on any day, on average, you can check, should have 0 return. There's no return to speak of on one day. But if you, on average, okay, I'm not saying that a stock cannot do very well on a single day, but on average, it should have just $0 return, 0% return. But if you look at a month, then well-established company, right, might have should have about 2% return. Maybe that's too much, but like 1% return or something on average. Okay, so that's to say that, right, the percentage the return should depends on what kind of window you're looking at. So for that matter, right, because we are really pushing delta t to 0, okay, or n to infinity, we need to modify the u and the d a little bit. So let u be, okay, e to the sigma square root delta t, e to be minus sigma square root delta t, all right? Why this choice? You'll see later, all right? But this is just one typical choice of u and d, and your homework has, you have done a homework on this before, with sigma, right, being the volatility, all right? So what I want to say is this, right? I want to see what Sn, right, the stock price at time n. By the way, right, the point of view is I'm not blowing up this picture to infinity, all right? I'm keeping the horizon fixed. I'm dividing, right? I'm subdividing the time points to find a point. So this Sn here is always like St, if you will, all right? So St, all right? I want to analyze how that behaves, okay, as n goes to infinity. All right. And the easiest way to do that is by taking the log. Because if I take the log, I will turn the product structure into a sum. So the log, okay, of St is log of S0 plus the sum of the log of Xi. okay? So basically then the limit as n goes to infinity of the log of st will be ln s0 plus the sum of the log of xi, okay? Now, what is this then? What is this object? Okay. Now, so the meaning of this, first of all, is very simple. This, right, if you want, I can bring this over here. Okay, I can bring this term over here. And saying that, right, log of st over s0 is the sum, right, limit. So what I'm saying is the log return during this period from 0 to t is the sum, right, of the log of these random variables in the intra period. Okay. Now, of course, again, right, this is a random variable. So there is some kind of conversions of random variable that I'm invoking here. What kind of conversions? Well, so let's look, right? If this is the xi, then the log of xi, right, will take value sigma square root delta t and minus sigma square root delta t. All right. And for demonstration purpose, let's just say they have probability 1/2 each. Okay. That's not really true. Do I want that? No, I don't want that. Sorry, that's fine. I don't want that. Basically, these guys, right, will have some mean, right? Some mean that depends on mu delta t, and some variance that's going to be sigma square delta t, something like that. All right. So just give me a moment here. One thing, right, that you might have seen before is that if you have a sequence of IID random variables, x1 up to xn, if you sum them, okay, and you scale them, divided by sigma square root n, okay, where mu, right, is the expectation and sigma square is the variance. So this is a sum from 1 to n. As n goes to infinity, this approach a normal distribution. All right. So when you mix independent random variables, as long as the mean and the variance do not blow up, then this converges to a standard normal. All right, or the distribution converges to a normal distribution. So the mean here and the variance here will not blow up. Why? Because when you sum up the mean, right, you got mu times t, right? The delta t here, if you sum over the mean, right? Delta t, if you sum delta t for I from 1 to n, for whatever n is, you always get t. All right. So if you sum up the mean here, you always get mu times t. If you sum up the variance here, you got sigma squared times t. So in other words, the mean and the variance do not blow up. And you're mixing these random variables. The result is this. The result is that when you look at the log, you will get, in terms of distribution, as a normal random variable with some mean that move with time and a variance that also move with time. That scale with time, sorry, right? That scale with time. All All right. Any question here? All right. So actually, you see, this result is very, very intuitive. And this is why I was saying that if you take a look at something very small, like delta t, and you look at the return, right? The result says that it's going to be a normal with mean mu delta t sigma square delta t. This is too small, right? Like 0.001 or something, right? This is too small. So on a very small time scale, the return seems like 0 to you. Or actually, the return is just too small to reflect. One more thing, right? One more thing, that these xi's are independent, which reflects on the fact that different periods, right, non-overlapping periods have independent returns. So when you take the limit, okay, what this reflects to is something like this. The idea that the x1 up to xn being independent translates to, if you have xt over s0 and s big T over s small t, they're independent. Okay. So in other words, right, what's going on here? This is the log return on the window 0 to small t. This is the log return on the window t to big T. Okay. From the discrete model, right, every x that goes into this guy will be independent of all the x that goes into this guy. So in the limit, they're also independent. All right. So any question here? So so the conclusion is this. If we, right, focus on the log return process, okay, basically we want to look at the log return of s sub u over s sub t for 0 less than t less than u less than big T. Okay, big T is the time horizon that we stop our analysis. Any tu, right, is any time points in between. Then we know something like this. Okay, is a normal distribution whose mean and whose variance is scaled with the window of time. For non-overlapping time interval, for t less than u less than v, this is independent of this. Okay, log returns over non-overlapping time interval are independent. These two characteristics together in the mathematical literature refers to, so besides the scale, all right, away from the scale, is exactly what people call a Brownian motion process. A and B, right, is, how to say this, right, is almost the characteristic of a Brownian motion. process. Okay. So what we do in terms of modeling, okay? So what we've done so far is to take the tree, all right, to take the tree, push the intra-period to 0 and see how the tree becomes. After we deduce that, focusing on the log returns, we get this kind of characteristic. Then we move away from it and just take a mathematical structure that is very similar to this and then model it from that point. And we'll return to the connection, right, after we understand the mathematical model. So what mathematical model are we looking at, right? Namely the Brownian motion. So the following is a precise definition of Brownian motion. Okay, so we'll refer to Brownian motion a lot in this class, so I just call it BM. So WT, okay, is a Brownian motion if it starts out at 0. WT minus WS is independent of WU minus WT for any S less than T less than U. This property is called independent increment. WT minus WS will have normal 0 T minus S distribution. This is called identical increments, or stationary increment. All right. So why stationary? It's because it says that the increment, right? By the way, the word increment means what? You hear the word increment a lot from now on. Increment means change, okay? A small change. A small change when time is changed a little bit. So increments refer to the change. It's a stationary because this increment is not a function of time in the sense that it does not depend on where we're at. Okay, notice it only depends on duration. In other words, the increment here, right, doesn't matter if S is 1,000,000 or S is 1, right? As long as T, the difference from T to S is, say, 1 point, then the distribution, right, of the increment is the same. All right, so what it says is like if the Brownian motion, right, so two things here, right, is from let's say from 0 to 1, and here is like 1,000 to 1,001. As far as probability goes, the change of here and the change of here are the same in terms of distribution. All right, that's what stationary means. It's stationary from here to here. Okay. Independent again means that as long as these two guys are not overlapping, then the change over here is not affected by the change of over here, and vice versa. All right. So anything with these three characteristics, A is not so much important, but B and C are referred to as a Brownian motion. Okay. Any question? All right. So we'll do a lot of work with Brownian motion, all right, soon. But now for a little bit, let's return to the log return, all right, of the stock. So notice right here, the normal distribution right here is exactly the stationary distribution, right? Stationary increment property. The independent here, of course, is the independent increment. So we throw away, right, the part 0. But you see, it's also clear because if u is equal to t, then this is natural log of 1, which is 0. So actually it matches here too. So we can model, all right, we can model the log return of st like this. Log of st over s0 will be mu times t plus sigma times wt. Okay. So again, right, let's show you that. And by the way, right, this is exactly the Black-Scholes model. Of course, there are a lot to learn about this. It's not just this simple, right, writing it out. But from this simple, like, kind of statement, this is the Black-Scholes model already. Okay. So what do we have here? We have several things, right? So the point of view is, right, taking this as a starting point, as a definition, proposing this as a model, okay? We want to show that it achieves exactly these characteristics that we conclude by taking the limit, okay? By taking the limit of the tree as delta t goes to 0. So, okay, what do we have, right? Right, when t equal to 0, right? Or, I mean, yeah, when t equal to 0, you should have 0 return, right? When t equal to 0, then the return, right, should be 0. But what is it? Mu times 0 plus sigma times w at 0, right? Which is 0, because w0 is 0, 0. Okay. B, right? What's the return between any 2 points? So for t less than u, right, log of su over st, right, is log of su over s0 minus log of st over s0. Okay. Well, which is going to be mu t plus sigma w, sorry, mu u, wu minus mu t plus sigma wt, which is mu times u minus t plus sigma times wu minus wt. What distribution does this have? Well, wu minus wt has normal, which means 0, and variance u minus t. That's by part C here. Okay. So therefore, right, this whole caboodle has distribution normal with mean mu u minus t, variance sigma squared u minus t, as we expect. Okay. What about the independent, right? So you see here, actually, it's quite simple. T less u less than v. From our previous work, right? From our previous work, the log return from the TU period is this. The log return from the UV period will be this. Now, pay attention, all right? The notation starts to get heavy, but these are the only random variables. Anything else are constants, okay? These are deterministics because this is a constant parameter. This is time. Time is constant, okay? Time is deterministic. So the only thing that's random is here. Now, if the interval is non-overlapping, the Brownian motion, right, will be independent of each other. The increments, the Brownian motion increments are independent. Therefore, right, so these two guys are independent. Therefore, the log returns are independent. Is that okay? Any question? So now let's go back, right, to the Black-Scholes model, which says the log return will be mu t plus sigma wt. Okay. Actually, then this also implies what st is. So a model for the log return is also a model for the stock price. Okay. So from here, you can conclude what the stock price is actually. The stock price then, sorry, what distribution of the stock price is. So here, right, you can conclude that ST has log normal distribution. You hear this a lot from the Black-Scholes model too. That basically, right, they say the stock price has log normal distribution. This comes from this analysis. And basically, right, the term log normal means that the log is normal right here. Basically, the log return is normal, or the log is normal, okay? So you can already do a lot of calculation with this, okay? But before we move on to pricing and all these kind of things, we have several questions to ask. Right. What is the percentage return in, right, the Black-Scholes model? So the percentage return, right, is ST minus S0 over S0, let's say, right? So you may think, well, that's easy, right? Because I know what this is. I know what this is. So I will, take this, plug in, and I get, right, exactly that is e to mu t plus sigma wt minus 1. That's easy. Well, not quite. What I want, right? Okay, of course, this is true, but so what we want to specify on, all right, is something that's moving to the realm of stochastic calculus. Where we want to specify, okay, the percentage return, and for that matter, okay, log return S, okay, the in relation with, sorry, the increments of time and Brownian motion. Okay. We'll spend quite a few times discussing this actually. In the end, you may see that it doesn't affect what we do so much in the class, but stochastic calculus is something that is bread and butter of the continuous Black-Scholes model, so we should talk about it. But the second reason is if you ever want to seriously discuss the idea of replicating portfolio in continuous time, then because the nature of the trading, right, is continuous, then without the idea of stochastic calculus, you won't be able to capture, right, the mathematics of how to do the replicating portfolio in continuous time. So let me clarify this, right? So for example, we have this, the log return is this. This is our model. Okay. So I will introduce this notation. So first of all, let me do this. The differential notation. D of the log will be mu dt plus sigma dwt. Okay. So this is one single term, one single term, one single term. All right. D of something, where D of something, okay, means, so okay, maybe let me clarify it a little bit. So if you're given a function of time, okay, so something that moves in time, which is a process, then dft means, roughly speaking, the change of f as time moves on a little bit for delta very small. Okay. So with this idea, what am I talking about here? Well, if you trace it out, what it means is this is log of st plus delta minus log of st, right? Because the function is log st, right? This is mu, right, t plus delta minus mu t. And then, right, this is sigma wt plus delta minus wt, which, right, you observe that this is just this. Okay. So, well, have we seen that before? Yes, we have. Right here. Right. So what I wrote down below is just exactly this version, moving u very close to t. All right, moving u very close to t. And somehow, right, not capture everything in terms of change. Okay, so here's I capture everything in terms of change. Okay, as time change a little bit, the Brown motion change a little bit. My log return, right? My log price change a little bit, which cause log return. If you prefer a finance interpretation, as time change a little bit, there's some disturbance in the market. There's some shock in the market, which cause my stock price to move, or which gives me my return. Okay. All right. So all fine and good. Except now, let's go back to what I was asking. I want to find the same language for percentage return. Okay. So here, notice, right? This is the language of percentage return for big T. All right, for big T. If I move T, right? If I move T close to 0, and I want to express, okay? I want to express the right-hand side not as this form, but as something that is in terms of the change of time and the change of Brownian motion. Okay, so I want to capture the change, the percentage return as a change of time and a change of Brownian motion, same as the log return story. Okay, so in other words, the log returns for the percentage return story, it will be this. I want this, okay, equals question mark dt and dwt. And you will see, right, this is a small change in stock price divided by the stock price gives me the percentage return, right? This is st plus delta minus st. Now, you may think, shouldn't it be this in view of this? Sorry, where was it? In view of this, right? In view of the log return, shouldn't the percentage return be the same thing? The answer is no. And this is where stochastic calculus is subtle. It will be this. If this is your log return, this is your log price, then the percentage return follows this. Okay. Now, what in the world is this saying? This is saying that percentage return is higher than log return. And that's a fact of life. Check it. If you have a stock price, if you calculate its daily percentage return, you always get a higher number than the log return. Okay. So that's not just the only story. All right. I'll stop here. But after explaining this, okay, we'll exactly discover the dynamics, okay, of how to put together change in time, change in Brownian motion to a change in the stock price, okay? And after that, we'll achieve our goal. One last thing is the change in Brownian motion has a very popular name called white noise. So if you want to look at that from that point of view, that's fine too. In other words, the white noise is what's driving, okay, your percentage return or your log return. And we want to know exactly how it drives these returns in this model. Any question? All right. If not, then I'll see you on next Wednesday. Okay. yes, this is where the material starts to get serious. You may think it's hard so far. Binomial tree actually is trivial. It's easy stuff. This is where math finance starts to be math finance. In other words, like all these stochastic calculus rules on displaying of prime motion is what makes it interesting and mathematics. So far, we've just been playing, really. There's nothing much. It's linear algebra. All right, yeah. Yep, cool. All right, talk to you later.